Welcome to the Unit 11 remediation packet, the guided practice. It says name the circuit symbols below. You should be able to recognize this as an ammeter. Ammeter. This right here is a battery or a source of voltage. And this right here is a fuse. Now it says state the purpose of each of the above components. An ammeter is wired in series and it is used to measure current. And current will usually signify with an I. A battery is the source of energy, otherwise known as voltage in a circuit, because the voltage is the energy per charge. And finally, a fuse is for safety. If the current gets too high, it will melt, breaking the circuit. So now it says convert the picture below into circuit schematic. You should be able to recognize that as a battery. Once you draw your battery, you draw your connecting wire. A light bulb is a resistor, and then you draw it to the other end. Sometimes people will draw a circle around this to indicate that it is a light bulb, but either way it's correct with or without the circle. Now, what is the water analogy for circuits? Just like water has to be kept in a pipe that's closed, electrons also have to be kept in a closed wire in order for the circuit to function. If there is any sort of hole in the circuit, what happens is those electrons can leak out and the circuit will no longer function. Almost every circuit schematic symbol has an analogous part in actual electric circuits. So now we look at this one. It says, what must the switch do for the circuit to function properly? Just justify your answer. So there's a switch right here, and there are actually two choices. My assumption is that in order to get the circuit to function properly, I want electricity to go to the resistor and the capacitor. If that is the case, I have to take and close the switch here. In doing so, I bypass this branch. In other words, no electricity will go there, but instead will go through the path of the circuit this way to the other end of the battery. Now it says which resistors will operate if the R5 resistor is removed. If the R5 resistor is removed, you should realize that R1 and R6 will still function. Next it says, what is electric current? Electric current, signified by I, is measured in amps and represents the charge per second. So it represents how much charge is flowing through a wire. A lot of people think of it as like velocity because it's a ratio of how much charge per time. Voltage, on the other hand, is the energy per charge. And so you can have a 10,000 volt electric current as your voltage, and it's still relatively safe because there could only be one electron. And that one electron has a really high energy for one electron, but that one electron is not dangerous in and of itself. The most dangerous thing is current. Now, voltage and current are related, as you see in Ohm's law. Generally speaking, the higher the voltage, the higher the resistance, or excuse me, the higher the voltage, the higher the current, unless you change resistance. That's why somebody who has wet hands is more likely to get an electrical shock than somebody with dry hands or with gloves on when working with electricity. It all has to do with the term resistance. So now the units for each of these: voltage is measured in volts, it's an easy one. Current is measured in amps, and resistance is measured in ohms. So now it says what happens to the resistance as the temperature increases. So as the temperature increases, the slope increases. So you have to be real careful looking at these. But if I look, the slope in this particular case is my rise over my run, which in this case is V over I. If I have a V over I can look at my formula and I can say V equals IR, divide both sides by I, and I can say, okay, the resistance is equal to voltage divided by current. So when I say the slope increases, what I'm saying is that the resistance increases. Now it says calculate the resistance when a 9-volt battery produces a current of 0.1 amps. And whenever you do this, if you do it correctly, you should get something along the lines of 90 ohms. Now it says calculate the power dissipated by the resistor below. The formula that I have for electric power is P is equal to IV. And what I have is I have a voltage source and I have a current as measured by an ammeter. So I could say 6 times zero point 0.3 and actually switch those. That's the current and that's the voltage, but it doesn't matter because you're multiplying them. And when you do this, you should get something like 1.8 watts. Okay, now when you have 1.8 watts, the next thing you have, it says calculate the energy in kilowatt hours. Kilowatt hours tends to be the unit of energy that we use more commonly, and the reason for that is because that's a joule is such a small unit of energy that generally it doesn't mean anything, so we tend to talk about things in terms of kilowatt hours. So the other equation that you have for power is equal to energy, which is any energy divided by time. Okay, when you have any energy divided by time, you can plug in your value for power and you can plug in your value for time, making sure you convert to kilowatts and that you convert to hours. Okay, if you do this correctly, you should end up with something like point zero zero 0.001 kilowatt hours. Okay, it's a very, very small amount. Now, it says if energy costs 15 cents per kilowatt hour, then how much would it cost to operate the circuit for 200 seconds a day for 5 days? So the first thing that I have to do is I have to recognize this is on a per day basis because it's that 200 seconds. So I have to multiply it by 5 to get 0.005 kilowatt hours in the 5-day time frame. Now I have the costs as 15 cents per kilowatt hour, and then whenever you do this correctly, you should get something along the lines of 0.00075. In other words, it costs less than 1 cent. Okay, next it says identify where the resistors are in parallel and when they're in series. These R1 and R2 resistors are in parallel with one another, and the R3 and R4 resistors are in parallel with one another. Now, when you combine those resistors, because resistors can be combined in parallel, the resulting resistors are now in series. So when I combine R1 with R2, it becomes that resistor, and when I combine R3 and R4, it becomes that resistor. The resultant resistance, once I combine those two, that is now in series because I have to go through both. Now, what is constant for resistors wired in series? Every resistor wired in series will have the same electric current as measured by an ammeter. So the electric current is the same in all of them because of conservation of charge. If I have resistors lined up, if I have one electron here, that electron has to go through the next one and it has to go through the next one. So because of that, whenever you have resistors wired in series, the current is always the same. Now, whenever you have resistors wired in parallel, what happens is the voltage is always the same. Now, I may not have the same number of electrons, but each one of those electrons is going to have the same amount of energy due to conservation of energy. So if this electron decides it's going to go this way, it's got 10 volts, but if it decides it's going this way, it doesn't all of a sudden have less energy. It still has 10 volts. And that's because it came from a 10 volt source. So next it says solve the circuit below for the current leaving the battery. Remember what we just talked about, how the voltage is constant in parallel circuits. If you do this correctly, you should get a current of 8 amps based on the fact that there's 240 volts in each branch. Okay, for the last one, you're trying to find the voltage drop in the R3 resistor, in other words, how much voltage is used. Remember, the current is the same in each one of these. So if you can find the overall current in the circuit and then the resistance right there, you should be able to find that the voltage drop in the R3 resistor is 1.29 volts. Now, you should go ahead and move on to the independent practice, and if you have any questions, please make sure that you see your teacher.